Okay, so please introduce Ilan Hirshberg, who will be from Ben-Gurion University, and he'll be speaking today on long thin covers and nuclear dimension.
Yeah, thank you. And sorry about the technicalities in the beginning. So as I wrote in the abstract, this is about some paper we put on archive a couple of weeks ago. That paper is pretty long; it's over 100 pages. Although we're hoping to slightly improve the things there and put a second version, which would also be over 100 pages. But so I thought, well, I can't really give a comprehensive talk about this in 2 hours, and you don't want to hear a comprehensive talk about that in 2 hours or more. So what I'll do, I'll give some sort of an overview, which some of you might have heard, and where I'll go over the main results, and then there's a coffee break. And then the subset of you, I didn't want to write proper subset in the abstract, but I will not be at all offended if people don't want to hear details, would say, okay, we had enough. But those who want to hear some more details, I picked one section from that very long paper, and I'll talk about a few more details about that, so you can have some because there are some new ideas there, and you can see how that works. I picked a section which is short, so we can actually go into details without that being overwhelming. Right, okay, so that's the idea. Okay, so let's see what's the motivating question. We have this notion of nuclear dimension introduced by Ilan Winter and Jochen Zacharias. It's a variation of this notion of decomposition rank, which was introduced by Hirshberg and Winter in 2004. Or appeared in 2004, and that's well, I guess Stuart is not here, so I can say that that's a very important concept in structural theory of C-star algebras. So I won't survey that. You've presumably heard enough about that. So one basic question, which is how robust this notion is under various natural constructions, particularly the one I was most interested in is cross products. And there's a lot of work on it for various angles. So just to put it a very general question, suppose I have a group, I have a C-star algebra which has finite nuclear dimension, and a group acting on it. Find conditions which guarantee that this cross product has finite nuclear dimension again. You can ask it more generally, does the cross product have finite nuclear dimension? The answer is, without any conditions, obviously no. This notion of nuclear dimension is a generalization of the notion of covering dimension for in the commutative setting. So if you have C of x, the nuclear dimension of C of x is exactly the covering dimension of x. So for example, if we take A to be the complex numbers, then that continuous function over one point that has nuclear dimension 0. Take the group to be something, let's say, z to the infinity, then which acts trivially on that point. Then the cross product is continuous functions on the infinite torus, which has infinite nuclear dimension. So it's to take a very trivial example that can't hold without any reasonable conditions. In particular, finite nuclear dimension also implies that A is nuclear. So if this cross product for whatever reason is not nuclear, for example, if G is not amenable and the action is not amenable, then that won't happen either. So we need some conditions, right? Okay. And in fact, we can also remove the question. I said, suppose A has finite nuclear dimension. It's also sensible to ask, what if A doesn't have finite nuclear dimension? And are there conditions which guarantee the cross product does? Now, I'm talking about finite nuclear dimension and not what the dimension actually is. Because there are essentially no known applications where we care what the dimension actually is, and in fact, in the simple case, it's known that the only possible values are 0, 1, or infinity. So it's not an interesting invariant in its own. The only question is whether it's finite or not. In the non-simple case, that's not true. Although there is some reason to believe that this is not an interesting invariant in its own. What's interesting is whether it's finite or not. Okay. It may be interesting nonetheless to sometimes have some bound which may not be optimal, in case, for example, you want to, that's a step in doing something else. Right? For example, if you have an inductive limit of C-star algebras, you know that the nuclear dimension of the inductive limit is bounded by the supremum of the inductive limits in the maximum of the inductive limits in all steps. So maybe if you, for whatever reason, have something which is going to be inductive limit of things, maybe you'd want to have some bound which is uniform, right? So maybe you have something simple in the end, but in the middle they're not. So you have to deal with that. I'll give some example like that in the second half. Okay, so this question has been studied, as I said, quite intensively, focusing as many things in C-star dynamics on the two extremes, either the case where A is simple or the case where A is commutative. What we did is a bit more general. We looked at C of X algebras. For the purpose of these slides, I'll talk about C of X. Although for the next half, I have to have the more general setup, which I'll mention there. Okay, so the question which motivates us now is suppose that X is some compact Hausdorff space, or maybe locally compact. We have an action on of some group on X. We want conditions which guarantee that the cross product has finite nuclear dimension. So here's a quick survey of what was known under various conditions for those kind of topological actions. Okay, so in the first condition, let's look at the actions of the integers. So G is the integers. We have X, which is finite dimensional. The thing which was studied the most in that setting was minimal actions, because they give rise to simple cross products. It's not clear that from the perspective of dynamical systems, minimality is such a natural assumption, but it is something which is looked at. So in that case, the first proof that cross products have finite nuclear dimension in this generality was in a paper of Thoms and Winter. They used what I listed there in the slide is kind of my titles for the techniques they used, which got used. Okay, so it's kind of a summary of what kind of techniques were used. That was proved using some sort of a large subalgebra technique, which goes back to some work of Chris Phillips or orbit breaking. This orbit breaking idea, which goes actually back to Putnam. So they had some technique involving that. It was reproved later in the as part of a paper I had with Winter and Zacharias in the context of Rochen dimension. So which I'll talk about. I'll go into in more detail. The idea is that there's this notion of the Rochen property, which comes from ergodic theory, that has a kind of a multicolored version, which is called Rochen dimension. We proved that two theorems: A, that if you have an action of the integers on something, or finite groups on something which has finite if A has finite nuclear dimension and the action has finite Rochen dimension, then the cross product has finite nuclear dimension. And there's also proof that all these that those for minimal actions of the integers, you always have finite Rochen dimension, free and minimal. Okay. Now this was generalized later in the work of Szabó to free actions. We actually don't need minimality for that. And it was further generalized from the case of the integers to the case of actions of finitely generated virtually nilpotent groups. So you can define this notion of Rochen dimension for residually finite groups. Makes sense there. But to get the proof to work, you need to assume that the group has a finite asymptotic dimension. So that boils down to polynomial growth in that setting. And so that was the best result for in the free case. Other approaches which came up in the minimal, going back to the minimal setting, is this notion of dynamic asymptotic dimension introduced by Gunther, Willett, and Yu, which is also somewhat related to Rochen dimension, although we have to kind of dig into it and understand why. It's really a groupoid notion. And so they have this notion of a dynamic asymptotic dimension of a groupoid, and they verified that if the groupoid is a transformation groupoid associated to a finite to a minimal system on a finite dimensional C-star algebra, a finite dimensional X, then it has this finite asymptotic dimension. And there's also this related notion of tower dimension due to David Kerr. So these some ideas can be used, could also be used to reprove this. The more recent approach, which gives the strongest results known now in the free minimal setting, is this notion of almost finiteness that goes back to work of Matsui. It was generated by Kerr and subsequently by Kerr and Szabó, and then by Kerr and Hirshberg. That approach is somewhat different. Instead of proving directly that the cross product has finite nuclear dimension, they prove that it's let's call it tracially z-stable, and that implies it's z-stable. And we know that z-stable in this minimal setting, you get a simple cross product, and z-stability is equivalent to finite nuclear dimension. Okay, so it's a different way of getting at it. And the advantage here is that you don't need this. You can get it for more general groups. The best results known at the moment are for free minimal actions of elementary amenable groups. Okay, it was first proved. It was done by Kerr and Szabó. Got it for sub-exponential growth, and Kerr and Hirshberg improved it to elementary amenable groups. Okay, so you get a wider class of groups. On the other hand, the downside is that it works. You need to assume minimality. It doesn't work in the non-minimal case, and all these things involve freeness. The group has to act freely. Now, some of those things work more generally, even if you don't assume that X is finite dimensional. I said that, so that goes a bit beyond the question I mentioned, right? If X is infinite dimensional, C of X does not have finite nuclear dimension, you nonetheless, the cross products may have finite nuclear dimension. So if X is, if the action, we have an action of the integers on X with mean dimension 0, Elliott and New proved that the cross product has it has finite nuclear dimension. They actually proved it's z-stable using again large algebra techniques. And this was improved, well, not exactly mean dimension 0, to actions which have some called topological small boundary property, which in the case of z actions will be the same, but for not exactly known as far as I know if what happens in more generally. Using this almost finiteness techniques. So that's the story here. By the way, I should say that the conjecture is that the cross product is z-stable if and only if the action has a mean dimension 0. But it's not known whether that's true yet. We have I have some work with Chris, which gives some examples where it's not based on some improvement of some work of Ilan and Kerr, but that's not part of what we're doing here. Okay, but it's still open whether for actions of integers, mean dimension 0 is the same as cross product having finite nuclear dimension in the minimal case. Okay, so what about the non-free case? Because everything so far involved freeness, right? And some of the things I mentioned, some things like finite Rochel dimension is actually some strong version of freeness, right? You have those kind of Rochel towers means that we have some things which get moved to something else, right? Those things imply the action has to be free. So what do we do when the action is not free? I mean, and as I said, you could say you don't care, but that would be a strange thing to do because many very natural dynamical systems which are studied are not free, right? I mean, it's quite common, for example, to even have something like periodic points might be dense. Think about, let's say, take the infinite product of a finite set. Look at the full shift. That's a very natural example of a basic example of a dynamical system. The periodic points there are dense. You don't want to say that we don't care about those. So this was settled in some previous paper I have with Zhang Wu, which goes roughly like this. We had some technique which is somewhat I'll call long orbit, short orbit method, where the idea is basically this. So to explain the idea of that paper, let me say what's the definition of finite Rochel dimension. So finite Rochel dimension means the following thing. Let's suppose I have this my space. Okay, let's think of this as being, let's say, the circle where it's attached. Okay, and suppose my action here is some translation or irrational rotation of a circle. So the Rochel property from ergodic theory means that you have some you have some space. You have this let's say a measure space, right? And you have I have an action, let's say, of the integers. You could do it more generally, right? And what you do is you can say that you have some you pick some n, and you can almost cover the space with those kind of blobs, which let's say this moves here, this gets moved here, and so on and so forth, right? And the remainder is small in measure. Okay, so that's the Rochel property. Okay. Now, and you could play with it if you want to and get the picture where you actually cover the entire space without any leftover if you allow two towers of different length. Right? You can't do it if you assume that the thing has length n and it covers exactly, because that would imply that you have some finite dynamical system as a factor. But if you allow two non-overlapping kind of towers of different lengths, you can actually do it without any leftover. Okay, that's not very important, but it's true. Okay, so you could try to do something like that on a space. Think of these, let's say, as open sets or closed sets, right? But first of all, if we're in the topological setting, not the measure case, you want to somehow, it's kind of, if we just want to take, let's say, projections, you can't really talk about a small remainder, right? The remainder would have norm 1. So that's not going to work very well. There are other ways of defining what's a small remainder, and that goes back to what I mentioned about almost finiteness. But our approach was to say, well, okay, let's suppose we have something where we can't really talk about projections. Let's say, let's say the circle, okay? Then what we do is, instead of like looking at sets, we want to look at some of its bump functions. So what I would do is, let's suppose I have this let's say the circle. This is identified with this. I look at the translation, right? Then I can say, well, okay, let's take this kind of bump function. It's moved here, and this moves here, right? Okay. Maybe. And then we are actually proving that those things don't look quite as too nice, but just for the illustration, let's draw it like this. So I might have this kind of thing. And let's even suppose I may not get exactly back to where I started, but right. I mean, if it's let's say an irrational rotation, I get here, and maybe when I go back, I deliberately miss this, right? So it would go back here. Okay, but I can come up with something like this, right? Okay, so I have this bump function, it gets translated to this one, and so on and so forth, right? Okay, and in the end got back almost where I started, if I did things carefully enough. And I should say it's not trivial to do things carefully enough, even for an irrational rotation of a circle. But leave that aside. Okay, now this is not a partition of unity, right? So I have those things which look like it's very trivial. I mean, the point is this dynamical system is somehow, if you ignore everything else, it looks very trivial. I have this, which gets moved to this joint set, and so on and so forth, right? The Rochel property tells us the Rochel lemma in dynamical systems tells you that up to some large n, your dynamical system is somehow very trivial, right? Let's have a bunch of disjoint sets which move to one another, and all the interesting stuff is how the last one goes to the beginning, right? So I have the same situation here. This gets moved here, this gets moved here, and so on and so forth, right? Okay. So for a while it looks like it's not very exciting, but this doesn't cover everything, right? I have a lot left. But here I can simply put another one with different color, right? Here's the yellow one, right? So this one goes here, this one goes here, and so on, right? So what I have here is this partition of unity, which is somewhat equivariant. They have the white ones and the yellow ones, right? And separately, the white ones are a bunch of disjoint bump functions which roughly go into one another, maybe up to some error, right? And they have the yellow ones which also do the same thing, the yellows ones are not disjoint from the white ones, but somehow the control here is overlap. The control can control the overlap, right? In this case, you have two colors. So any point can be non-zero at most two of those. And of course, you could have higher dimensional verbs. So this is the definition for the action of the integers. We say that the action has Rochel dimension at most d if for any epsilon and any n is the length, how many bump functions they have, right? I have a partition of unity, which consisting of I have two indices here. I have a lower subscript, which tells me how lower index, which tells me how many the length of each tower, and the upper index tells us how many colors there are, right? You have d plus 1 colors, and what happens is that each one goes roughly into the next one, right? Up to epsilon norm, where this, let's say, is cyclic. So when I get to the end, they go back to the beginning up to epsilon, and any two bump functions of the same color are basically disjoint, or at least almost orthogonal. Okay. I mean, I'm allowed to. It's okay if they overlap a little bit, but not very much. Okay, and as I mentioned before, Gabriel proved that for free actions of finite dimensional spaces have finite Rochel dimension, even has the bound. Okay. Okay, so now I don't want to say what's the proof that those cross products have finite nuclear dimension, but you could imagine that it would involve, if you've seen a definition of, I haven't defined finite nuclear dimension, but it involves some approximations. But if you've seen what you could imagine without having read the paper, although I'm sure you all read it, is to you'd imagine that the proof has to go something like this, right? I mean, the definition of finite nuclear dimension is that you can approximate the identity, right? It's for any finite set. Maybe I'll call this kind of B. For any finite set F, and for any epsilon, there exists this type of approximation, right? It's approximate approximation, right? So we have CP map going down and CP map going up, which are this map would be d plus 1 decomposable, whatever it is, right? And such that this diagram computes up to epsilon on this set F. Okay, that's the so as you might imagine, right, where somehow we want to use this finite Rochel dimension to prove the theorem. So what we will do is we would have some finite set in this A would in this case be the cross product. We would have some epsilon. We want to construct those maps which give us this almost commutation up to epsilon. For that purpose, we somehow use this finite Rochel dimension in some way, right? So as you might imagine, and this is what happens, what would happen is somewhere in the proof we would say, okay, so we have some tricks for doing it, right? We have those Rochel towers, and we somehow which have some parameters in them, right? They have like well, the number of colors is somehow given, right? But we have this length of a tower, and we have this epsilon which comes there, which might be different from this epsilon, right? Okay. So in order to construct this approximation for this particular set, for that particular epsilon, we need Rochel towers of length long enough, so and so, right? And we need some accuracy there. And having those things, we can construct the approximation we want, right? If I want a better approximation or like a smaller epsilon or a bigger set, I might need to pick different parameters there, right? Okay. So you can think of a quantitative version of a quantitative version of Rochel dimension, right? If I don't want to approximate everything, but only a particular finite set to within a particular epsilon, I would need to know that I can find a given those Rochel towers with a given n and a given error here, not all. Okay, right? So we just need to and now it turns out if you stare at it, if you want to prove this, right? Okay, we know that finite Rochel dimension to get that, the action has to be free. But if we want to get this very limited version where we can find Rochel dimension with of length n and error epsilon, then you don't need the action to be free. You just need it to be free enough. Okay. And you could just prove it if you want to using ultra filters or something, right? You just if you prefer not to write an actual proof, or if you like logic. So right, so it has to be the case. I mean, so okay, so what we did is this. So let's maybe I'll finish describing this method before I move on. So the idea is this, right? We can somehow say, let's take our space, right? I want to approximate a given to do constructive approximations for a given finite set f to a given epsilon, right? I figure out what length of orbits I need to exclude, right? I need Rochel dimension of length at least a given n to within a given tolerance, right? Having now that I know what length I need, I know what the minimum orbit which is allowed. I mean, right? In order to get Rochel towers of length at least 1 million, right? To within tolerance so and so, I need to exclude orbits of length at most something, right? Okay, as long as I know that there are no orbits less than 1 billion, I'm fine, right? Okay, and then you say, oh, okay, so what do I do about the I can break up my space in two, right? I have an open invariant set consisting of all the points which are acted on either freely or at least they don't come back until the 1 billion years passed, right? And you have the ones which have a small orbit. The ones which have a small orbit are a closed invariant set, right? And then we somehow deal with them separately. With the bit with the long orbits, we have this Rochel dimension basic part, right? For the bits which we have where the orbits are short, you simply analyze it directly, and you realize that, well, the cross product of that part, that's some sort of subhomogeneous C-star algebra. You understand it, and then you just need to somehow stitch those two parts together. So that's the idea, right? It's a bit and so that takes care of the case of integers, and we're happy about it to some extent, but it's a bit ad hoc, right? Because when we're done with that, we said, okay, let's do it now for z squared, right? I mean, why not? And then you start thinking about z squared, and you realize, well, things are a bit more messier because when you have an action of the integers, then you know, well, I have two when you take a point, they have two options. Either it's periodic or it's not. And if it's periodic, I have a certain length of the orbit. So it makes sense to talk about a short orbit or a long orbit. If you have an action of the integers, well, okay, sorry, of z squared, and you pick a point, you might act on it freely, but maybe it's free in one direction and not free in the other, right? You have lots of different directions. So just trying to take that into account and trying to make sense of this or have some sort of breakup which would work looks like a nightmare, and at least we had no idea what to do with it. So it looks like that method was very specific for the integers and also for the reals. We have a version of that for the reals, which is more technical, but it can be done as well. But at least for z squared, that idea doesn't seem to work. So instead, we decided to develop a more systematic approach, where what we did is we defined some general notion of dimensions for an action, which we call the long thin cover dimension. And we proved the following. If we have an action on some locally complex Hausdorff space, and we know that this long thin cover dimension, what we call dim LTC, is finite. And now we also have to take into account, I'm not talking about free actions, so we have Gx as a stabilizer, and various points might have stabilizers. We somehow have to just assume that the group C-star algebra as well as the stabilizers has finite nuclear dimension, and in a way which is uniformly bounded, because otherwise, you see the definition. I mean, if we have a group acting trivially on a point, this dimension will be finite, right? So, but the group C-star algebra would appear, right? So you have to somehow have that part of the assumption, then the cross product has finite nuclear dimension. Okay, and in case you're interested in a bound, we actually have a more precise bound, which I put here. It's a product of 4 things, and I told you we're working on an improvement. So because we realized after posting the thing on archive that we can remove one of those, so we only be a product of 3 things. It would streamline the proof a bit, so we'll may as well do it. It's a product of the long-term covering dimension, the supremove of the group of the nuclear dimensions of all the group C star algebras of all point stabilizers, and the what we call the asymptotic dimension of the coarse orbit space, which I'm not going to define it because that's bounded by this LTC dimension. So we could have made this squared at a time the dimension of x, but we actually can remove that. This +1 is simply a short way of writing +1 for everything. Okay. Otherwise, you run out of space and it's hard to read. But when you look at dimensional estimates, you always have this annoying +1 thing. Okay, so that's our theorem. And of course, you say, well, okay, that's a nice theorem, but who cares about this long thin cover dimension?
Can I just ask how much is one effect to be true in the converse case?
So if
the dimension is nuclear dimension is finite.
But that's surely false, because this implies this LTC dimension, if that's finite, it implies that the dimension of X is finite.
Yeah.
So so we know that we have action with 0 mean dimension. This does not cover those. Maybe there's some improvement we don't know about, some asymptotic version of that. It would be interesting to do, but the way it stands, we strictly assume X is finite dimensional.
How easy is it to isolate this and see this as an example?
Well, so you can read the paper, but so yeah, we need examples. It's not, I can't say there are any easy examples, but we verified it for various classes. So here, so I'll go over the classes we verified it for. One class is groups of polynomial growth. So if we have a finitely generated group which has polynomial growth, which is the same thing as saying it's virtually nilpotent, that's the famous theorem of Gromov, then we know, and the space is finite dimensional, then we know that this LTC dimension is finite for any action with no restriction. Okay. So this now the second condition we need is, I'll talk about what's in the middle in a moment, is this thing about point stabilizers. But here we can use this theorem of Eckhart, Gillespie, and McKinney. They showed that the group C star algebra of a group which is finitely generated virtual nilpotent has finite nuclear dimension with the same bound on all subgroups. That's the combination of those 2 things gives us that, basically improves the result from the case of the integers to the case of actions of virtual nilpotent finitely generated groups, in particular z to the n. Right, these all have finite nuclear dimension with no restriction whatsoever in the action. We actually do it in 2 steps. We define this kind of notion of large-scale packing constants for groups. It's some group theoretic notion, and we kind of ask some group theorists if they've seen that, and they said us that they haven't quite seen that. So I don't know if that's interesting to them or not. And we proved that this long-term cover dimension is controlled by those large-scale packing constants in a way which somehow depends on the dimension. This is what we mean by that, by these packing constants. So it's not the precise definition, it's almost precise. The point is how many balls of radius r you can put in a larger ball of radius capital R plus R. Okay. So you can think of some, I give you a radius, I draw a ball, okay, I draw a ball of radius R plus R. And the question is how many disjoint balls of radius r can you put there? What's the maximum number? That would be the 0th LSP dimension, roughly. Okay. And but we can also have we might have some higher dimensional versions of that, which will look at how many of those I can pack when I actually allow some overlaps. So maybe allowing some overlaps, but for example, maybe you say that it's you do some dimensional version where maybe I'm okay with, let's say, its most any point can be in its most, let's say, 3 balls. Okay. So if any point can be in its most 1, that would be the 0th version. If any ball can be in its most 2, that would be the LSP1 and so on and so forth. Okay. So you could ask some question where some packing where balls are allowed to overlap, but not too much. Okay, so that's this idea. And this time it comes up when we just have to do some bookkeeping. Okay. Now the second class of things we can cover are actions of hyperbolic groups, or boundary actions of hyperbolic groups, or more generally, so things like the action of a hyperbolic group on its Gromov boundary. There's some higher dimensional versions of that, but it's the same proof. That's actually done also in 2 steps. We basically rip off some work of Bartlett and Reich. They proved that these types of actions have, well, we introduced some notion we call the equivariant asymptotic dimension. It's relative to a family of subgroups. I'm not going to define that. It's something they basically studied with a somewhat different name in a slightly more restricted setting. And we show that the LTC dimension is controlled by this equivariant asymptotic dimension relative to a given family of subgroups, times all the LTC dimension of those actions of those subgroups. Okay, the subgroups turn out to be the stabilizers, right? So for an action of a hyperbolic group on the Gromov boundary, the stabilizers are virtually abelian groups. So we know that actions of virtually abelian groups are virtually abelian is in particular virtually nilpotent, right? So, or actually they're virtually cyclic. Sorry, they're virtually cyclic. They're virtually so this we know how to bound by our previous results, right? And so we have this thing. So we have this thing in general. We have this is known to be finite in that context by also very long, very involved paper of Bartlett and Reich. It's also several 80 or 90 pages, and which they use for a different something else. So this combination gives us this LTC dimension in that setting and covers those examples. Okay, and the last thing, which is what I'm going to talk about in the after the break, for those of you who decide you're haven't been tortured enough and you want to hear more, is this recently introduced notion of allosteric actions. There was recently some paper of, I mean, as I mentioned, there is those techniques of almost finiteness, which work well in the free minimal setting for larger class of groups. Apparently, there are some proposed generalizations of that to actions which are what's called which are not quite free, but topologically and essentially free. So in general, it's known that if you have a group acting on a space, the resulting C-star algebra is simple if and only if the action is minimal and topologically free, not necessarily free, right? That's result of Archibald and Spielberg. So there's some work trying to adapt this almost finiteness techniques to that setting. I think it's not published. I haven't seen it yet, but but in any event, any action with this almost finiteness condition has to be what's called essentially free, meaning that if I have, suppose I have furthermore an ergodic probability measure on my space, an action is said to be essentially free if the set of points with non-trivial stabilizer has measure 0, and topologically free if it's meager. Okay, so if right, so if the complement is density delta. Now, and it was a question for a while whether there are examples which are topologically free but not essentially free. So they're almost free in this topological setting, but you have a set of large measure where the stabilizer is not trivial. So Joseph constructed those things several months ago. We had some, I mean, we don't quite know how to deal with his examples. We have some idea, but it doesn't fall into our framework. But we constructed other examples where we can deal with them. In particular, we have examples of Reith products of finite abelian groups by Z to the D. So for example, the Lamplighter group is a Reith product of the Z2 by the integers. So we have some profinite action of those, which we can show are allosteric. And an application of our techniques, not direct, but not very indirect, can handle those cases too. Okay, so that's the summary of what we have there. Now, I should give you some definition. So here's the definition of the long thin cover dimension, and you can see why you don't want to hear about it. So as I said, it's a bit technical. So I'll try to go over that, and then we'll have a break. Good thing. So you'll show you a scary definition right before the break, so you can escape. And so, okay. So it is kind of like a Rochlin type thing. Okay, not exactly, but it somewhat resembles it, which is adapted to the non-free setting. So, so maybe before we go into the definition, maybe I'll show you a picture. So the thing that illustrates it better and it's nicer than the definition. So what we have is this. I have this is my space, right? I have some what I do is I want to somehow cover the space with these kind of collections of blobs, right? Each collection of blobs. Now notice I'm not claiming that the each blob goes into the other. It's not this picture of the not exactly this Rochlin picture. Think of these being supports of bump functions, right? If I have one bump function which goes into roughly into this bump function, it doesn't mean that the support of this goes exactly into the support of this, right? I mean, it might be close in some sense, but it's not exactly right. So in some sense, I have this collection of blobs, which in some reasonable sense mimics some partial orbit. So I drew in black some sort of if you take a point, you follow it for a while along the group, right? Here the group is integers, right? And I have to stop at some point. So I have some given length in the group. I use it to follow around some point. Okay. And then I have some sort of collection of blobs or somehow close to that, right? Okay, and I could do that also when they have those periodic orbits, for example, right? Here I have 3 points, so you have to go around, and I have those points which somehow go around. And notice that, of course, I'm not saying this blob goes exactly here, and even deliberately, it's obviously not, because I even put the point outside one of them here and inside one here. It's not a mistake, it's deliberate, right? So this might happen, right? But I have those kind of sets which somehow, in some sense, mimic or approximate this kind of fattened up version of this orbit in a way that the following things are true. And maybe I'll go over it before showing you the proper definition. We're going back to the other slide. The idea is, first of all, this thing has to be long. What do I mean by long? Long, what it means, we have a certain length, right? And we say that if we take any point, not necessarily one of those black ones, right? They take any point and they follow it along this given side of the orbit, right? Okay, let's say it's length 5, right? I'm going to have some blobs which contain that, right? Right, and this will continue, and maybe the orbit here goes outside, but I'm going to have right. So if you give me any point and you move it around the orbit, it's going to be covered by one of those collection of blobs, right? Which is labeled by something else, right? Those points are the labels, right? So these track something else, right? These track maybe some orbit here. Who knows what, right? Okay, so these things track something, right? And which, you know, and these might diverge at this point, right? Maybe those white ones go here. Okay. So if you give me any point, right? I'm going to have some collection of blobs which covers those, those are actually inside. The second thing is that what we call is thin. Thin means that, you know, the diameter of each one of those is small, including this label. This is the label, the thing we track, right? I want all of these to be in a small diameter. Okay. Let's look at the rest of the definition. Okay. So this is what we call the long part, right? That any partial orbit would be in something, right? I'd have the instead of dimension, so things might overlap, right? I mean, I'm going to have a bunch of those. So maybe I have some other one. Like this, right? So I'm going to have some overlap with the blobs if it's the cover, but the multiplicity is controlled, right? So not any point could be at most d plus one of those blobs. I have this lambda is what's called this labeling function, where you picked some particular orbit which we're tracking, right? That's the that turns out to be better than labeling Rochlin towers by group elements. Instead of labeling them by group elements, we label them by points in some chosen orbits. It turned out to be nicer to work with. This is the thin, as I said, the diameter is small, and we also have this technical addition saying that, you know, okay, it's long, but not too long. We somehow, you know, we limit the number of blobs we have. Okay, so, okay, maybe I'll talk a few minutes about the ingredients proof, then we'll have coffee. So let's talk about the proof that C of X has finite nuclear dimension when X is in the non-dynamical context, when the group is trivial. So that's easy to do directly, but I want to slightly complicate the regular proof and describe it like this. What I would do is say, well, okay, I have this finite collection of functions in C of X. I want to almost approximate it using this decomposable approximations. What I do is, first of all, I forget about the topology. I simply have a natural mapping of C of X into L infinity, right? Okay. And then what I do is well, I mean, L infinity is too big. I simply pick some reasonable collection of reasonably dense points inside of that, fatten each one of them up, make sure they don't overlap too much, and use those to construct bump functions to go back up. Okay. Now, of course, if you actually want to write a proof, you'd skip this part because you'd just pick the points to begin with, right? Okay. But I want to present it like this because this somehow gives a more streamlined or maybe it's easier to see how things ought to be generalized. Okay. So we first, step A, forget the topology, and then you put it back in using these kind of we forget some points, and then most points, and then we somehow use the reasonably dense ones to put things back together. Okay, so in the dynamical setting, you simply want to make all this roughly equivariant. Not exactly, because there are infinitely many points, but roughly. Okay, so here's the free case. Okay, that's not our case yet. We talk about the non-free case, but in the free case, what we want to do is we want to have a group acting on everything, right? We have a group acting on C of X. It also acts on L infinity, right? You could have the same type of picture. Now, only the things become more complicated because now what you want to do is instead of looking at the point, you have to make things equivariant. You have to look at an orbit or at least a partial orbit, right? That's some long enough part of the orbit, right? Now, when I make this discrete, what happens instead of having L infinity, which is basically this discrete, you know, this thing of dimension 0, what happens is we have some disjoint union of things which look like the cross product of G on itself, right? If it's a free action, any point, the orbit of each point looks like G. When I forget about the topology, it's simply a copy of G, right? And so we have this uncountably many invariant copies of G acting on itself, right? And the action, this cross product is what's known as the row algebra, uniform row algebra, right? So we simply have lots of, so instead of having lots of different points in the infinity, I have lots of different copies of the row algebra. And those row algebras have, are known to have finite nuclear dimension. The nuclear dimension of those are bounded by the asymptotic dimension of the group. That goes back to the original paper of Winter Zacharias. And then we need to somehow patch those together, right? I said before we have this cover, right, with overlaps, and I use those bump functions to put them together. So what Rochel dimension really does is give you almost equivariant covers, bump functions, right? Instead of having one bump function, you have a collection of those, which is almost equivariant, which looks like, at least insofar as you're concerned, for a finite number of elements in the group, it looks like it's kind of equivariant, right? And that's used to somehow patch them up, right, to put them up together. So it's an equivariant version of that very simple-minded original proof. In this, it's not exactly how it appears in that paper, but if we had to rewrite it now, it's how I write it. So now, so we could say, well, okay, let's just do the same thing. Why do I care that the group is acts freely? Because if it weren't free, then I wouldn't have copies of the same algebra here, right? What I would have is, for various points where the action is not free, it's going to look like G acting on Ilan infinity of G modulo the stabilizer. Okay. So I'm going to have all manners of different orbit types appearing there. And there might be infinitely many of those. It might be unmanageable. We don't quite know what to do with that. So we had some way of dealing with that, right? So so the first attempt you might do is just, look at Ilan infinity, G acting on that. Just you try to use that instead. You realize that there are too many things there. So we had this idea of saying, well, and this is really this more conceptual version of what we call the short orbit, long orbit version. We somehow replace. We have this particular set of elements we cared about. We started with some, S, which is what we looked at, right? We always start with a finite set of elements, and what we do is we replace the stabilizer Gx by the stabilizer as seen by those elements, which is simply the intersection of the subgroup generated by the intersection of the stabilizer and S, right? Because S is finite, so now we have a finite number of groups, so that makes things much more manageable. Now, why is this the same thing as short orbit, long orbit, really? The idea is this. Let's think about the situation where I have the integers. Right, okay? And let's suppose that for whatever reason here is 0, and let's suppose I care about these elements, right? Okay, so I'm somehow looking at things which involve only those elements. I don't really care too much. Maybe if I only look at those, I might care about some iterations or something, but I somehow know how far I care, right? Okay. And now suppose I have something which is okay, so I have those points here 0, 1, and 2, okay, and anything more than 2 is a very large number, right? So suppose I have something which is stabilized by this, by 5, right? Okay. Now 5 is a huge number, right? Now if I live here, right? Okay. As far as I'm concerned, and action is stabilized by 5, as far as I'm concerned, the action is free, right? I mean, yeah, it's going to come back in 5 years, but that's so in some sense, what do? You say, well, we separate things we take each stabilizer, right? Okay, we look at the intersection with these points, right? And we look at when we replace, we have some method of replacing this subgroup by what's seen there. And what happens in this case is, if the stabilizer, of course, in the case of the integers, things are kind of trivial because each stabilizer is generated by 1 point, right? You look at the minimal orbit, right? So if the minimal orbit is here, as far as we're concerned, it's a short orbit. If it's outside, as far as we're concerned, it's a large orbit, right? We just we treat it as though it's free for the purpose of the argument, and that works. Okay. Now, and of course, if the group is more complicated, the kind of orbits you might have are more complicated. But this is basically the correct replacement. The way we go back from infinitely many cases to a finite number of them. Right. We also have some replacement for asymptotic dimension, but Okay, so let's go have coffee. And those of you who want to hear more can come back.
So thanks for coming back and we'll resume.
Yeah.
Hear more about nuclear.
Okay, so thanks. So okay, so maybe I'll give the statement of the main theorem I presented before, just so we have it on the board. So suppose we have and I didn't talk about CFX algebras, but I'll need it now. So only a very special case. So let's suppose the so suppose A is a C0 of X algebra. And if you haven't thought much about C0 of X algebras, think about simply things such as, a bundle of matrices over C of X. That's good enough for us. And suppose alpha is an action of group G on A such that the induced action on C0 of X, I mean, let's suppose the center or something has finite long thin cover dimension, then the nuclear dimension of A plus one version is bounded by the product of the LTC dimension of alpha plus one times the dimension of X plus one times this asymptotic dimension.
What cross products?
Yes. Of what's called this coarse orbit space times this supremum of the nuclear dimensions of the cross products of fibers by their stabilizers, by the point stabilizers of X. Okay, so before when I wrote the statement, these were points, and I had the group C star algebra. But in general, you might have a fiber bundle over X, in which case the fiber would be invariant, but may not be fixed. So the stabilizer acts on the fiber, and you'd need to assume that these are finite and uniformly bounded. Okay, so yeah. Okay, so okay, now for whatever reason I'm calling it gamma now, so I'll stick to what I have in my notes. So what I want to do is to outline a construction of allosteric actions, which is somewhat different than the one, or a generalization of something which appeared in Joseph's paper. I'll simplify it a little bit, so we did something a bit more general than this. And then I'll show how we can use the techniques we had to control the nuclear dimension of those cross products. And that's something which is not amenable to actions of to other methods. So okay. It's what we call the coarse. I'm just using notation here, but it's what we call the coarse orbit space. I didn't define that. If you want to, all of these are bounded by this, so we can write this cubed.
Yeah.
So this cube times S. And as I said, AX is the fiber. So I have right. Okay. So if X is fixed by a subgroup G sub X, then that acts on the fiber of this C of X algebra. And I have to throw that in as an assumption. Okay, so what I'll do is I'll give some general theory. I won't go into all the details, but I'll at least say how we what are the tools or what are the tricks we use. So okay. Okay, they said for whatever reason I'm calling the group here gamma instead of G, so I'll stick to gamma on the board so as not to confuse myself. So suppose we have so suppose gamma is residually finite. And countable. And suppose let S be some non-trivial group element. One, I guess. And let's suppose and fix some delta between 0 and 1. Okay, so now suppose I have this that's residually finite, so suppose we have some sequence of sorry, backwards. I have a sequence of a decreasing sequence of subgroups, such that the intersection is trivial. Okay, you always have that if it's residually finite, but that's the definition. And consider. Okay, so consider gamma acting on gamma mod n by left translation. It induces an action of gamma on the inverse limit. Okay, that's what's called a profinite action, right? Okay. So okay, so the theorem here is, so suppose we have this fixed element S and this fixed delta. So suppose that for any n, the set of all elements with a Q in gamma mod gamma n, such that SQ is Q. Let's suppose that this set has cardinality at least delta times the cardinality of this quotient. Then this profinite action is logically free, but not essentially free. Now, essentially free is with respect to a certain measure, right? Here, this action is actually uniquely ergodic. You can, so it's not hard to check. So there is one obvious measure. It's simply counting measure in all of these, right? So each one of those has a counting measure, right? Those actually intertwine counting measure, and that's an invariant measure. Okay. So counting measures on each factor set that induces a measure on X, which is invariant with respect to this action. And what we'll show, which is actually fairly easy, is that if we have those conditions, then this action would have some, then the set of points where the stabilizer is not trivial would have measure at least delta. X is the inverse limit, yes. Yes, it's basically some improvement of his method. So if it's essentially what he used. So if you look at his paper, he didn't write it like this. He had more conditions. So he basically, what we did is we simply stared more carefully with his methods. He had some kind of more delicate construction, and after we looked at his method, we realized that you don't need to be nearly as careful as he was. You can simply if you, okay, so when you think of something the first time, the way it is, but when you look at it more carefully and you somewhat analyze his method, you realize you can be much more coarse in your techniques and cover more examples. Yes, but it basically goes back to his ideas when you just simply stare at his paper more carefully. You seem to disagree. Okay.
So you can cardinality list of points which are fixed by
This givenness, yes.
Well,
It's a particular fixed one.
Yeah.
Okay. Okay. Now, of course, the question would be why do those exist? But let's first say why do those conditions imply that? Then I'll give some general condition. This we can prove easily. So I'll prove this. The rest I won't prove. I'll state because, but I'll show how it works. Okay. So here, okay. So let's see how this works. Okay. So first of all, what is this projective limit? Well, you can think of it as a sequence of elements, right, or rather factors, right? So this X is things that form or sequences. Let's say H1 gamma 1, H1 gamma 2, H2 gamma 2, and so on, right? Right. So all sorts of cosets, right? Okay. Right, where they have to be consistent, right? So when each time when I factor by a larger group, this has to be the same thing, right? So in other words, such that so I guess Hn, if I take Hn plus 1 and you look at the mod gamma n, that's the same thing as Hn gamma n for all, right? That's this consistency condition. Okay, so it's a subgroup of this, so it's a subset of this infinite product. Okay, so that's the definition basically of this projective limit, right? Okay, so okay, so let's see what it means for an element to stabilize this. Okay, so for G to stabilize a point like this, right? So let's call this, I don't know, H bar. Okay, this sequence with respect to given the right. So G H bar is the same thing as H bar if that's true for any one of those coordinates, right? And that's the same thing as that's if and only if for all n G H n gamma n is Hn gamma n, which is the same thing as saying that Hn inverse, if we conjugate G by Hn, that's in gamma n. I want to just mention that just because to give some idea of what would be involved, because you can't construct such examples for something like for an abelian group, right? Because that would never happen, right? But somehow you somehow want those kind of subgroups to be very far from being normal for something that's to work, right? To have those fixed points. Okay, but in particular, if you have any element in the center of the group, for example, 1, the trivial element, then nothing is going to fix it, right? Aside from the trivial element. So in particular, so the stabilizer for the 1 okay, let's call this I know E bar. This is the stabilizer that is trivial, right? G, the stabilizer is just trivial, right? Okay. Okay, but the second thing to notice is this action is obviously minimal, right? I mean, it's the orbit of any point is dense. You can see it easily, right? Particularly the orbit of this point is dense. And if you have 2 points in the same orbit, their stabilizers are conjugates, right? Okay, so any point in the orbit of this point it has a trivial stabilizer, right? Okay, so therefore all points in the orbit of this point E have trivial stabilizer. So we have a dense number of points, a dense set of points with trivial stabilizer. Okay. All orbits are dense. Now, as for G delta, that's always true. So it's if you think about it for a moment, not just for this action, for any action, right? The set of points with trivial stabilizer, that's always for any discrete group action, that's always a G delta set, maybe not dense, right? Just because no for G delta, simply say that for any G difference in 1, the set of points x and x, such that I'll write the action as G times x. It's not x, sorry, this is open. Right. Okay, and so the set of points with trivial stabilizer is simply the intersection of those, so that's G delta, right? Okay, that's true for any dynamical system, any group action. Okay, so this shows it's topologically free. Now, as for on the other hand, for essentially free, well, that pretty much shows you it's not, right? So the condition we had about the size of S, if you track it down, it shows you that the set of all points which are stabilized by this particular S has to have measured at least delta. Okay. I mean, it would be some intersection of some decreasing intersection of sets, all of which have measured at least delta. So the intersection has measured delta, at least delta. Or okay. So it's not so if we can do this, it's not essentially free. So how do we do this? Because the integers are essentially finite, and you cannot do this. So we can construct allosteric actions for Rieth products. What's a Rieth product? So here's a construction of such actions for gamma, which will be I'll write z to the d, although it would because that's where we can prove things, but or more generally. Instead, so I'm writing z to the d because later on I do need it, but for the action for the construction don't need it, and this would be finite. Abelian, we don't need finite exactly. It's good enough if it's abelian and residually finite, but for the proof we need for later on we need for it to be finite.
Did you do any of these conditions in order to define the Rieth product? Or
no, for the Rieth product, don't need anything. If you do for two groups, so should they just define the Rieth product in general? So the Rieth product in general, let's call this G for now. Thing. Let's say 8 abelian just so that's used additive notation. Okay. But you could do it any 8 abelian G. The only thing is you see is this, right? We seem to look at we consider C0, 0, GH. This is all the finitely supported functions from G to H. Okay, that's an abelian group under addition. Well, if G is not abelian, then just use a multiplicative notation, right? That's a group, okay? So all the functions from G to H, which are trivial outside the defined number of coordinates, right? Now we have a natural action of G on this by translation. Let's say left translation, okay? So G acts on it by translation. By translation. And this Reith product is simply shorthand for writing is defined to be the semi-direct product of this by. Okay, so if you haven't seen the definition, that's the definition. Okay, so the idea which we do, which I'm not going to go through the details of how we do it, but you just have to verify that these things can be done. It's a matter of, at this point, it becomes an exercise to see it can be done. So the idea is to fix we fix our delta and fix okay, I used H and G backwards in my notes. So I'll try to count for that or switch it here. Okay, so let's take consistent. So let's put those in G. That's an increasing sequence of finite sets. Okay, G is countable, you can do it. Let's suppose that we take this and suppose G1, G2, oops. So suppose we have this decreasing sequence of subgroups of G, are finite index subgroups. Of G, such that have the following conditions. First of all, we'd like En inverse En. Okay, I'm not assuming it's abelian. We want this intersect Gn to be trivial. And secondly, we want them to be more and more sparse, right? It's something which this is not hard to do, right? Because we pick those things successively, right? So suppose we first pick those exhausting increasing sequence of finite sets, right? Now I get to pick those decreasing sequence of groups, right? So what I want is, first of all, okay, I know what the set En, I know what this set is. I want to basically to miss Gn. It's easy to do, right? And secondly, this is just a certain number of cosets, right? A certain number of points, right? And I pick Gn later after I know what those points are. So I think we want to pick Gn to be sparse enough so that this is a small number of points in this larger coset space. Okay. So you seem unhappy about this.
I understand that you can do it for kind of one end, but
no.
I mean, think about the integers for this purpose, because maybe instead of making g could be, it's interesting when g is the integers, right? In this case, so think about the integers, right? I give you some collection of finite sets and some collection of finite subgroups which are already reasonably sparse. Okay, right? What I want to do now is, okay, so here, maybe here's the integers, and maybe here's one subgroup, right? Okay, and which maybe I fattened it up a bit because there's some finite set here, so maybe it includes, like, let's say any two things which are around this, right? And maybe I have some larger set E2, right? Which maybe is maybe it's this, right? And all of this translates with some sparser subgroup, right? So maybe this and this, right? And maybe something else larger with some sparser, but I know things in advance, so I can just, make things sparse enough, right? And now I need to pick something which is sufficiently sparse so that there are enough of those gaps to make up more than epsilon of what's left. Okay, right? I mean, remember that, okay, only apply this to Ilan to a larger one. So you might worry that, this is going to be covered, but no, because I made sure that I picked the next one to be so large that this will not, right? This gap will be large enough. So yes, so I mean, it's basically an exercise for the integers, and that's essentially the main case of interest. Okay, so having picked those things, the construction would be which is this. No, the ends are given, right? If you want to, but right, but given ends, pick the GN. I mean, we're allowed to pick both of them ourselves. I think it doesn't really matter how you pick the ends. You could pick you just simply need to make the GNs more and more sparse. Much more, in each successive stage, you have to make the next GN sparser. Sufficiently sparse, not sufficient.
All right, so using a finite n inverse EN as a finite set, a GN big enough that you have condition one.
That's easy. That's trivial. That's trivial. And but you also need to make it much sparser so that you have enough gaps left.
Know what this union is.
Well, you need to have picked it before to make sure to be careful to make sure that you left enough gaps. But yes.
Okay.
But you kind of know there are enough gaps before, right? Right. I mean, each successive stage you left a delta percentile of gaps, right? So at each point you somehow need to add something which doesn't cover too many of those gaps.
Okay, so you can't just naively say, suppose you have any G1 up to Gn minus 1.
Well, they have to satisfy this. The moment satisfy this, you're okay, right? Because you have more left, right? So you're going to, right? So this is less than this, right? So now you're going to, well,
it would not work.
No. It would not work if you had less or equal. If you had less, then each time you can add a little bit more. Okay. Well, you could make it less or equal to just because you know it, but in particular, yeah. But the idea for the construction is right. Yes, you keep having to have a bit more, right? Okay, so we could probably write it as a series or something if you want to put. Okay, so now the idea is, so suppose we have this basic setup, which that's easy to do, okay, right? Notice this is just about this group G, right? Which which you may well think of as integers, right? It said Z to the D, but make it Z if you want to.
You're saying that you want the long thin dimension to be finite. Why wasn't You know, the only reason I can think of why it wouldn't be true, even if it were infinite, is that some of the other things were zero. And the left-hand side.
Well, the other thing can never be zero because they have this plus one. So if it's zero, that will be 0 plus 1. So none of those could be less than 1.
I mean, the other thing.
Yeah, all of them are at least 1. All of them are at least 1. None of them can be 0.
Right.
So
Okay, so
it
then you
just
don't
says,
need, then
it
you
just
don't
says
need,
your just less than equal to eight.
you don't need the long thin dimension to be final.
Well, it's a trivial statement in that case, yes.
Well, we have to take time for people to sort that out.
Well, okay. I mean,
And that
yes. I mean, we don't get an interesting statement if it's in.
took me between then and now.
Yeah. Okay. Yeah. No, it's true, but it's yeah.
Okay, well, good.
So okay. So now what we do is we have to look at the let's set we'll call it n sub n in C00 of G H by as follows. This will be
H is anything,
H is that find abelian group.
any finite abelian.
Yes. We could do that for residually find abelian, but I don't want to bother. We have to change something for that, and it's not interesting enough to do. So this will be the set of all f's in this C0 finally supported functions, such that condition we need is the GQ. This will be 0, and that will be for all j from 1 to n, and for all q in EJ. Okay. So we want those things somehow when I average over the group, I want to get 0, but only for elements which come from this J set. So for E1, for any element in E1, which comes in E1, I want the average over the group to be 0. For anyone which comes in E2, the average over the group G2 would be 0, and so on and so forth. Okay. Right. So in this picture, for any no, so for maybe I should have put the quantifiers first. Okay. Right. Okay. So in other words, think of those. Right. I mean, what I have here is functions from here to the finite group. Right. Let's say the group is E mod 2. Okay. Let's say the group is E mod 2. H is E mod 2. Okay. So I'm counting parity. Right. So if I take, let's say I have this, like, this particular subgroup, which is a standard up version of the white points, right? So I have this kind of finally supported function. Maybe it's sometimes it's 0, sometimes it's 1, right? And there's a finite number of 1s, right? Okay. So what I'm saying is that, okay, if I look at the translates, this, right? There's only finitely many of those anyway where it can be non-zero, right? Okay, so if this H is V mod 2, the parity has to be it has to be even, right? Okay, so on the translates of this, if it's 1 here, maybe it's 0 here, maybe it's 1 here, but it has to be 1 an even number of times. Okay, and if I look at one of those things which are here drawn in purple, right, then the same thing has to be true, but only for translates along the that larger group, right? Which in particular applies to this too, right? By the way, because okay. So so we have this condition, right? And oops. Okay. Okay, so what I'm saying is this subgroup H n sub n, this is Gn invariant. And we set subgroup gamma n to be n sub n dn. Okay, so this is our sequence of subgroups, and then you have to check that those conditions hold. Okay. Okay. So let's leave the theorem here, just so we can finish seeing what I wanted to do. Okay, so let's consider the case where we have a profinite action of actually it works for any profinite action. So if gamma is H wreath product z to the d, H is finite abelian. Then any, and this is a profinite action. Then the cross product has finite neutral dimension. Okay, so let's see why is this the case. So okay, right. So so we have here an inductive limit action, right? So C of x is an inductive limit of C of gamma mod gamma n. Okay, now in each case, each one of those, I have an action of gamma mod gamma n, sorry, of gamma on this finite set, right? So so it is enough to have a uniform down to the nuclear dimensions of each one of those, right? Okay, so on the nuclear dimension of C of gamma mod gamma n, semi-direct product gamma, because the cross product is an inductive limit of those things, right? Now, what are those? Now, C of gamma mod gamma n, cross product gamma. Well, this we can write as C of gamma mod gamma n cross product by, I mean, we have a semi-direct product. So here we'd have C 0, 0 of z to the d with values in H, and z to the d acts on this. Okay. Now, so what's this? So here you have to stare at it a bit. It's a very simple thing. It's this group, which looks a bit nasty, but it's not too bad, right? It's a Pointryagin dual is a Cantor set, right? And it acts on some finite sets. So you think of it for a little bit, you just see that this cross product is simply some C of X algebra, not X, let's say C of Y algebra for Y the Cantor set, and the fiber is matrices of size osmosis. Y is the Cantor set. The fibers are matrices. Right, matrices, the different sizes of matrices which come up are something like the orbit sizes you get here. So that's controlled by this number. Okay, okay. Okay.
Oh, okay. Oh, C0 and CD.
Yeah, that's a group.
I was confused on the notation.
Yeah. Yes, I mean it's an infinite direct sum in the algebraic sense of the group H, right? Okay. So it's not finitely generated, but actually understanding this course is very easy, right? That's going to be some C of right? Yes. Okay. So now we have now we're basically done. Now we just we know that for arbitrary actions of Z to the D on the Cantor set, we have finite length and cover dimension, and we simply throw it into that machine and we're done. And the reason I wrote this long estimate rather than saying it's finite is that we needed a uniform bound, and we get the same bound regardless of what n we take. Okay, so that's how we can use those techniques to cover those allosteric actions as well. Okay, so maybe I'll end here.